a pleasure to be here, really. I'm going to be very different from what you've heard. We are going to be talking into a different field, as you will see, and hopefully it will have a future with this audience and others. I'm going to be talking about PCSK7. You understand, this is proprotein convertase subtilizing kexin. It's a family that we discovered. There are 9 members. The odd numbers are interesting because the numbers 7 and 9 are going to be the ones we're going to talk about. First of all, I'd like to thank Jean-Charles Fouchard and Jamila Fouchard-Najib for their kind invitation to attend this meeting. Thank you. So this is the family we discovered. It took me 30 years to do this. But it is a member, there are 9 members in this family. We all talk about PCSK9, but there are other members, you know, that are, to me, as important. Today, I will be talking about really mostly the PCSK9, just a small word, but really I'm going to concentrate on number 7 of the family, which turned out to be an enzyme that can cut at basic residues. This is the PCSK9. When it was discovered, we didn't know what it was doing. We knew it was in the liver and so on. And this is the effect on a primary hepatocyte in human. If you put an inhibitor like evolocumab, you will see the increase in the LDL receptor. It's just a Christmas tree. You don't need a PhD to see this, you know. And you can see the increase in the LDL uptake by the cells. So clearly, this inhibitor is very functional. Now, how does it work? We all know, we all use PCSK9 inhibitor without really understanding the mechanism by which PCSK9 drags the LDL receptor and other receptors to degradation to lysosomes. It took us another 10 years to figure this one out, okay? And it turns out to be a complex situation whereby PCSK9 binds a protein called CAP1. It's a cytosolic protein, which bends it in such a way to expose an M2 residue, an M2 domain at the C terminus. And it also binds by the catalytic subunit, the LDL receptor. The M2 domain recruits an MHC class 1. Now it puts us into the realm of cancer, it puts us in the realm of immunology, you know, whereby this whole 4 proteins together will go to lysosomes. So there is really a participation of a number of proteins for this protein to be functional. And so I want to give an acknowledgement to Jean Davignon, who has been my mentor. This Pandora's box was for us for a long time. We're trying to figure out how things work. And he's the one who made this slide, and it's the last tribute to him. And basically, when we discovered PCSK9, many things appeared, you know, and it's continually appearing. We just discovered that PCSK9 degrades the receptor of COVID, as an example. And this is how it regulates inflammation. And now people are injected with a monoclonal antibody if you are at the hospital and being intubated. And 50% have come out. This is the latest clinical trial. So it has multiple applications, and we'll still have to learn what are the partners of this protein. Today, I'm going to be concentrating on another enzyme, which we call PCSK7. This is the beauty of north of Canada, the kind of animals we have, you know, and unfortunately disappearing at high rates. The enzymes of the 7 first enzyme, furin and so on, they play major roles in activating of a number of proteins, of which PC7 is a member, and it activates proteins like the metalloproteases, anthrax toxin, and so on. But really the only substrate that is specific for PC7 that no other convertase can do is the transferrin receptor, because it sheds it. And that's in clinic. You can see people who have a large amount of circulating transferrin receptor have usually a change in PCSK7. And we've proven it biochemically and so on. And there was a SNP that appeared by a GWAS study that showed that people who have that SNP have more PCSK7 and they have more transferrin receptor circulating. So that was, if you want, our background. We then asked the question, well, what is the relationship of that SNP, which regulates iron, okay, and cardiovascular disease? And we knew there was a connection between iron and cardiovascular disease. And so this is a recent GWAS study that we performed over almost 300,000 people here. And what we saw, again, it strikes you, a direct correlation between increase in PCSK7 and increase in triglycerides, increase in PCSK7, and increase in apolipoprotein B. Well, what is that? How does that work? Okay. What about the reverse? And so we had patients in our institute who were coming to be tested for their triglycerides, and they had all pancreatitis and others. And we have screened a number of them and sequenced 6 of them here. And of the people we have sequenced, 2 of them, the number, this number 6 and number 2 turned out to have very low transferrin receptor. That hit us, and it says, oh, this could be a relationship to PCSK7 after all. And they had ApoB in the 5th percentile, low ApoB. That was, and so we asked the question, well, what about if we look at it in mice? What happens if we remove PCSK7? What happens? We knew that because for years we had done this. And we obtained what is known as the cool mice, because these mice have lost anxiety. Okay? They actually process brain-derived neurotropic factor less efficiently, and they have less anxiety. That's great. But to get a drug to go through the blood-brain barrier was a problem, and many anxiolytics already are there. And so we began to ask the question, is there a relationship between anxiety and lipid metabolism, and metabolism in general? And so what we did, we took our cool mice, as we call them, and we looked at the ApoB. We knew from the GWAS studies that maybe there could be a relationship of ApoB when there is a loss of function of PC7. And indeed, we find that about 50% less ApoB circulating and in the liver of knockout mice, which live very well, by the way. Like PCSK9, they live long. The triglycerides in the liver were lower. But the question is it a question of larger secretion of the VLDL from the liver, or is it uptake, or what? So we added, of course, the inhibitor of the lipase and found that actually VLDL are secreted less, not more. So the loss of ApoB is not due to higher secretion. All right? What does it do to the lipid droplets? What does it do to the liver accumulation of the triglycerides? And man, this is really happening. You get a smaller lipid droplets and you get lower amounts. And the lipid droplet size is actually smaller. So there is a connection between loss of PC7 and loss of triglyceride in the liver. All right. Well, how does that work? Okay. Now, what we asked the question was, what if we do the reverse, right? We're going to overexpress PC7. In this case, we use primary hepatocytes from human, overexpressed it, and lo and behold, you get more ApoB secreted. So PC7 somehow helps ApoB to get out of the cell. Okay? We think it's a chaperone, but we'll come back. And does it require activity? Because, enzymes like furin and so on require activity. We have inhibited the activity of PC7. You don't need it. So this is like PCSK9. It's acting non-enzymatically. This is the only other member, aside from PCSK9, that acts non-enzymatically. That was the first thing. The next thing was, okay, what happens if we remove it? So now we removed it by siRNA in HepG2 cells as well as IHH cells, and made a CRISPR generation from PCSK9, PCSK7 cells. When we lose it 100%, again, we're getting about 50-55% less ApoB. This is real in many cell lines, in mice, and now it's happening. How? Well, we think that when you do that, the cells don't like that. They're going to go into something called unfolded protein response. Okay? But it's actually, you will see that this is beneficial. I mean, people tend to think an unfolded protein response is always bad. I don't think so. I think the cells is trying to react. It's trying to correct the situation. And this is called, and we see that the increase in phospho-ERK and IRE1 alpha. We think that that should lead to enhanced macroautophagy, and it does. Okay? As we know from the classical use of this unfolded protein response. And that would lead, we show, to beta oxidation. So what's happening is the loss of PC7 somehow put a temporary stress on the cells, which leads to beta oxidation. And we think that that's what's diminishing the triglyceride that we're seeing. All right. How does that work? And when does that work? Okay. We do the typical cyclohexamide where you block translation from RNA and ask the question, how long does it take for ApoB to disappear? But it's very fast, in minutes, okay, when you put the cyclohexamide. Within about 10 minutes, you've lost most of your ApoB. So that tells you it's probably a proteasome. And indeed, if you put lactocystine, a proteasomal inhibitor, wow, you get a lot of polyubiquitinated ApoB, which we know will happen if you use an MTP inhibitor. This is what you will see. Okay? But now what we're seeing is in PCSK7 knockout cells, you get a lot of ubiquitinated ApoB if you block the proteasome. Now, is it really the proteasome? Well, we tried different inhibitors, autophagy, Brefeldin A, and so on. It's really the proteasome. It's only the proteasome that if you inhibit it, you lose the loss of the ApoB secretion. All right. The next question is, which part of ApoB is implicated in this PC7 interaction? Okay, so we've done a lot of work. I'm just saving you the time. We've created a short, what we call ApoB21, with the mutation that everybody uses here, ApoB48, 48%, and here is a 21% size of ApoB. We're looking at the N-terminal part of the ApoB. And lo and behold, that's the one that is implicated with PC7s, the N-terminal part, the first 200 amino acids of ApoB. If you overexpress PC7, you get more ApoB. You don't need the activity of PC7 because you block it. You get the same thing. And if you look in the medium, you get exactly the same thing. So it's the N-terminal part of the ApoB that is somehow talking to PC7. We don't know how. Well, do they actually talk to each other? Really? So we co-immunoprecipitated them, and we do see a direct co-immunoprecipitation of ApoB, the short form, and PCSK7, as well as the long form. All right? So they bind to each other. That's great. This is cells. And what happens, as we all hear about the lipid droplets and accumulation of lipids and so on, so we can take those IHH cells, incubate them with, this fats, if you want, olive oil and so on, and they will accumulate lipid droplets. There's no problem. But what happens if you have a CRISPR, PCSK7? They don't. Okay? So clearly, the absence of PC7 prevents the accumulation of lipid droplets in those cells when you challenge them with a high-fat type of environment. All right? What about this PC77L mutation that we identified in our patients that had lower ApoB? Is it proteasome also? Well, we figured this one out. We think that PC7 is a chaperone of ApoB. It binds to it, takes it out of the ER, allows it to get out. And if it has a change of amino acid in the cytosolic tail from a valine proline to a valine leucine, this, for cell biologists, they know a lot about leucine, dileucine motif, it's called, okay? It is a trafficking signal. It tells them, go to lysosomes, okay? So what's happening is that if you put a PC7 with this mutation that we find in human, there is much less PC7 and much less ApoB. They go to lysosomes. So they get out of the ER, but instead of getting out, they now missend it to lysosome. Like we've seen in PCSK9, some mutants where they actually been sent to lysosome much more efficiently. All right, so we think that the PC7 deficiency leads to ApoB degradation by the proteasome. This is what I showed you. And that the mutation here, which according to our calculation is about, there's 108 people who have homozygote mutation like this in the world, if you go to the GNOMAD database, and that enhances the degradation in lysosomes. All right. Can we reverse this? How can we use this clinically, So when we give a high-fat diet to a mouse, they get fat. All of you know this, I'm sure, multiple papers here. You get fatty liver, you get accumulation, you get steatosis. What happens if you remove PC7? You still get steatosis. So it doesn't look like the absence of PC7 prevents the formation of fatty liver, but it looks like it prevents in the recovery. So this is what we discovered. So what we do, we induce steatosis by giving a horrible diet, high-fat, fructose and glucose and cholesterol. And you can see, there's no doubt, there is an increase in the NASH diet, as we call it, wild type or knockout. You get a total amount of lipid droplets, the number and the area and so on. But then we say, okay, you've got your McDonald's food, now we're going to stop you. You're going to go into a diet. We're going to prevent you from using this food. Okay? And now we give them a recovery of about 4 weeks. Look what happens. In the absence of PC7, they recover way better. The number of lipid droplets go down. They go up, actually, because they're smaller. The mean area is down, and so is the total area. So we think that what PCSK7 does, because it increases the beta oxidation, it actually allows the liver to get rid of the excess lipid. Not only that, the animals lose weight at a much faster efficiency in the absence of PCSK7 when you go to what we call the recovery diet. So the conclusion of this work has been that PC7, loss of it, does not protect from the induced diet for steatosis, but facilitates liver recovery from the steatosis. All right. So what about pathology? So we gave this to a pathologist who completely blinded and tell us what's happening. And clearly you see the increased pathology, the ballooning and so on, and the steatosis score when you give the diet. But in the absence of PC7, the grades of steatosis and ballooning are way better than the wild type. So there is some hope that this could be an approach. So what happens to the liver situation? What about the AST and ALT levels? Look at that. They go back to normal, after recovery, whereas the wild type mice don't. The liver is still suffering. You still have higher ALT levels. So the absence of PC7 prevented recovered the lipid droplet levels in a safe manner because the liver recovered to a normal situation. We then went to a lipidomic analysis and did all the lipids by mass spectrometry to find out what is happening in terms of the composition of the lipids of these livers. And you can see that the composition of the liver in the recovery becomes almost equal to the non-treated animals, whereas the wild-type animals still suffer a lot by huge amount of increase of C18, C20 lipids, and so on. So there is a change of program. It is reversible if you have no PCSK7. Great. So we think that altogether, this suggests that the loss of PC7 reversed the hepatic lipid perturbation induced by the diet. Great. So what is the model? The model is that PC7, we believe, is a chaperone that binds ApoB very early on in the ER, allows it somehow to fold, different from the MTTP, different from the others that we know. And if you don't have PC7, well, what do you get? You're going to get the lipid, it gets ubiquitinated, ApoB, that we have just shown you. And then what happens? Lipids cannot, they're accumulating. You have to get rid of them. There's no more ApoB to take it out. Okay? So this creates what we think an adaptive, unfortunately, not maladaptive, it's an adaptive UPR. People tend to think of UPR always as bad. It could be quite good for proteostasis. It's an adaptive UPR which leads to autophagy, beta oxidation, and we think that would lead to enhanced lipid degradation. So can we use this now in a very way that we can lead this to clinic, as this can be used to clinical application? So we thought about it, of course. We're a clinical research institute, and thanks to Jean to have really incited into me this thinking, which I'm not a clinician. And so we've decided to make antisense, because it's happening in the ER, we cannot use inhibitor. And first of all, you don't need enzyme activity for this. We have to use an ASO, an antisense oligonucleotide. They're stabilized and so on. And we've attached a trivalent galactosamine, which binds the receptors in the hepatocytes, which are the galactose receptor, So we've given them a horrible diet for 17 weeks. They became steatotic, and we allowed them to recover, okay? And we've gone through the whole system. We've screened a number of ASO, picked up 2 of them, and compared them to vitamin E, which is what is treated right now as it stands with these patients. What happens? We get the same thing. Here we go. Number 7 really recovered. Okay, look at it. Now it's going down in terms of the total area of the lipid droplets, in terms of the mean area, and in terms of pathology. Look at this. ASO for the hepatocyte ballooning is in stage 0. Okay? The inflammation is in stage 0. Even the steatosis group is getting better compared to the tocopherol or to the wild type. Clearly, removal of PC7 just with an ASO. So we would think that, this was a knockout of PCS7. It's in every tissue. Well, how do you know it's in the liver? This is liver. Okay, this is directed to hepatocytes, actually, against the ASGR1 receptor, which is the receptor of galactosamine. Now, we have not really devised this experiment to do fibrosis, because you need to give more cholesterol a longer time. But already at that stage, we can say that fibrosis has improved, okay, in both ASO2 and ASO7. Actually, it turns out that the tocopherol also improves a little bit the fibrosis of these mice. So we can conclude that here's the big wow, okay, that the simple oligonucleotide injection for 4 weeks after this horrible diet brings down ApoB by 55%. It's not zero. It's not like mipomersen where you go down to zero and you get fatty liver. Here you get 55%. That's the difference. Okay? So we think that PC7 or PCSK7 has both protease dependent because it sheds transferrin receptor, but also independent in the triglyceride regulation. Now, I haven't shown you, but some years ago we showed that it enhances ApoA5 degradation. This is how you can increase lipoprotein lipase activity because you are by removal of PC7. Because you're increasing ApoA5, so you're getting more lipase activity. And it now facilitates the ApoB secretion. We believe it acts likely as a chaperone. Now, ASO are apparently very safe. In fact, the animals PC7 live almost to 4 years of age. They're actually very happy, you know. They're not anxious and they live longer, okay? And so we can do that. But now what's interesting, and again, I'm looking for patients, for medical doctors like you, which I'm not. And I'm told that one of the big problems is homozygous FH. Homozygous FH have a lot of ApoB, as you know. And one treatment is the mipomersen. There are some problems with mipomersen, as you know. You can get fatty liver. We believe, and we've proven it now in mice, which are LDL receptor knockout mice, which resemble this, treat them with this ASO may be another approach to diminish their ApoB in a relatively safe way. This is what we're thinking right now. So I'd like to thank everybody that participated here. We are on top of our institute here. We pray to God that our grants get accepted, our paper get accepted, you know, and we really, this is the team that without them I would not be here. Vatsala Sashan, he's the one who really pushed this whole project all alone, with the help, of course, of everybody else. We need funding, of course, the CIHR and the Fondation Le Duc, who really supported our work. So thank you very much.